Good. So before we go to after the tool length compensation, before we go to the tool radius compensation, I would like to add the zero offsets, because at the moment we are just moving our machine in machine coordinates, basically in the coordinates that you define the kinematic model in, and that makes it difficult to machine the box that we have defined as a part, since machining the part makes sense, of course, relative to the offset. So first of all, I would like to define a G54 as a zero offset for the machine. We will also make use of the transformation concept, and in the future sessions of this course I will show you a different mechanism that allows you to link the zero offset to the geometry view of the ONT. But the first approach that we will take is a little bit simpler. It will basically allow us to define the zero offset directly in the ANSI program instead of querying it from the ONT. That is also something that of course works on the real machine and is pretty popular in some industry and some use cases. So on the Siemens controller, to activate a zero offset, like on many other controllers as well, you use G54, and to actually define a zero offset and define the position of the zero offset, you use system variables, and that can be programmed on the Siemens controller with $P UI frame, and then in square brackets the number of the offset, and 1 represents the zero offset for G54, 2 would be 55, and so on. And then an equal sign, and then a C trans for an offset, trans for translation, so that just means an offset, and then in brackets I would like to have an offset in X direction by -100 and one in Y direction by -325 and one in Z direction by -530. So that's how I define the zero offset, and with G54 you can activate it. So I just save the program and simulate it to see how our simulation reacts if it comes to this code. And in this case we should get an error message telling us that CSE, or the parser, has recognized $P UI frame as a variable based on the equal sign, so that is basically a variable assignment. So CSE has identified that, but it doesn't recognize the variable $P UI frame. So that's something that we have to define first. We do that in Machine Configurator, and we go to the Variables tab, and similar like we defined the $P tool P, we define an additional variable, call it $P UI FR, and in this case on the Siemens controller it does not support single variables like the $P tool P. The Siemens controller also does support arrays, and you can see that with the square brackets. So in the square brackets you basically have the index of the array. So in this case $P UI frame is an array. Then if you switch between single variable and array variable, Machine Configurator shows you the capability to define the dimension of the array, so how many values can you store in that. And on the Siemens controller you have up to 100 zero offsets, so that's G54 through G59, and then it can be continued from G500 5 to I think 599 or something like that. So there are many of them. So we define the array size as 100, and then we need a type of the variable, and in this case that's a very special variable type, one that exists only on the Siemens controller. So besides standard variable types like boolean, character, double, integer, real and string, the Siemens controller has two specific variable types. a data type called axis and a data type of frame. So those two will only be available in Machine Configurator if you select the Siemens controller as a data type. And so in this case I need the data type frame, and we will see later on what the data type frame actually means and what it does contain. We know already that it obviously is capable of storing a transformation in 3 coordinate directions, but we will later on see that the frame is even more powerful and can handle also rotations and even more. So this allows us to define the variable. So I just save it, save my MCF and run the program again. And in this case the assignment works. I do no longer get an error message. Of course the G54 is not defined. So we will now define a G54. And we have seen that we've used one of the transformations for the tool length compensation already, the $tool transformation, which is built in. And we will use a very similar mechanism also for the zero offset, and it will prove out in the end that this is a very powerful mechanism to define all kinds of offsets, not only the fixed zero offsets but also local offsets. For the tool length compensation, that's something, a problem that you have on every machine. Therefore we have a built-in transformation, the $tool. For the zero offset, that is something where you can define your own transformations, and you do that in the transformations tab in Machine Configurator. And here with a right mouse click you can insert a transformation. In this case it's a linear one. We will see what the other one can be used for later on. So we need a new linear transformation and just give it a name. In this case we use the name fixed for the fixed zero offset. And if you look at the CCF files, you will find out that the transformation fixed will be used in also the FANUC or the Siemens CCF file for G54 zero offsets. So we've just defined that the transformation is really just defined by the name, so there are no additional properties that you can configure here for linear transformations. Next we go to the Commands tab and define a G-code with an integer, call it G54, and put it here in the right order. Now we can directly start to configure the code. Since if we think ahead, we will find out that we probably also need G55, 56, 57 and so on, and that they will be very similar. We can actually start to write a method for that, and the method will have just a single parameter. The only information that we need to know is which zero offset should be activated, and we can use the D1 here, for example, the index. So for G54 we can use the offset number 1, for G55 offset number 2, and so on. So that will be the parameter that we can use for the method. So I will go to the methods domain and add a new user-defined method, call it GME set fixed transformation, and edit it. Like I said, I will need a parameter, and we can call that offset ID or offset number. And then, similar as for the tool length compensation, we will need the transformation commands. If you look that up in the documentation again, you find it, where is it here? Transformation, activate transformation and reset transformation. So we need Activate transformation. The first parameter will be the name of the transformation, and in this case it's our self-defined transformation called fixed. Then we first have to deactivate it. In the end we will have to activate it. Then in between we have to reset the transformation to clear it. And now for the tool length compensation we use displace origin and then defined an offset in one coordinate direction. Since the frame variable, or this $PUI variable of type frame, already contains offsets in multiple directions, that would be inconvenient to query all the offsets and apply to all the axes. So, and for this we have a special function, and that's one of the functions. Since the frame type is really Siemens specific, it belongs to one of those kernel commands that extend the general functionality controller specifically. So in the Siemens 840D you find a couple of commands, or couple of kernel commands that are really only available for the Siemens, and one of these functions is this one is it, set trafo by frame. So we set the transformation with the values from a given frame variable, and that's what we will use. So I copy that, put it here. Then the first parameter of set trafo by frame is again the transformation name, so that's fixed, that's correct already. And now we will need to get access to our variable $PUI frame, and in this case it's an array. And to access array values, there is in the variable section, so far we used set variable and get variable, and for arrays there is a set array element and get array element. So in this case we will use get array element with the array name and the index that we want to have, and to read out the values and store it in the transformation. So we type get array element, and then the parameter is $PUI frame, and the second parameter is actually our offset ID, offset number, and that should do it. So let's close it. Yes. Of course, we've just created the method. In G54 we still need to use it. So I need to call method, select it from the list, and then here type the correct offset number. In this case for G54 it's 1, and I can copy it just to show you how that works. Make a G55 and type 2. There's one remark. If you make changes here in the edit fields, you should press the return key, otherwise Machine Configurator will not take over the change. So that's important to know if you're working with Machine Configurator. So I'm saving that, and then we can test it. So I'm activating G54, at least we don't get error message, and now I'm moving to XYZ0. So far we didn't move at all with this command, and in this case we are moving to this position. And this is what I measured out before. If you measure the distance between this coordinate system and the machine 0, which is in this case for this machine the center of the spindle in this position, if you measure that, that's exactly these values that I keyed in here before. That's the 0 offset for the machine. So that's a pretty nice way to define offsets and work with and use the transformation concept to define a 0 offset.